Right, let's see. What we're going to discuss today, as I'm talking, I'm recording this thing, what I'm recording, what I'm doing, the presentation. I might give it to you later to follow it up if you read one. We're going to look at functions. Yeah, I think the most important thing today, let's talk about functions. Then later we're going to look at different types of functions. Now guys, when I'm saying functions, you can see, all of you, that's the word in plural, that what we need to understand first of all is what is a function. I hope at this stage you should have noticed that in life in general, we deal with things we can call variables. Now things will change, maybe change with time or change with situation. Like for example, one example of a function I can talk about, when you're coming from home today in the morning, obviously there are two variables involved. You moved, covered the distance, d, therefore distance. But as you're moving, covering distance, there was another variable involved. Which one? Time. So you've got there time. Now, as we are talking about functions, this is exactly where we come now. When now we start to look at the relationship between the distance and the time, then we'll talk of the distance we're covering as a function of time. In other words, the distance we're covering depends on time. That's not the definition of function. I'm just giving you an example of a situation where we experience what we can describe as a function. Are we together? So now we can then later say distance covered, let's use L, is L of t. Now as I'm saying, the length you've covered or distance you've covered is a function of t. Then it can be described by a mathematical expression which could be maybe a t plus maybe some c. That's an equation, you know, isn't it? And then this is the equation of a line. Then we should say the distance being covered there is a linear distance, isn't it? It's a linear function. All together. Okay. So I think it's clear now. We've just said if we're dealing with a function, there are variables in what concern. So the function, one variable will be a function of the other. In other words, normally in mathematics, we use the word f for function. Then we say a function of x, and that's normally we use y. Say y is equal to f of x. Now y is a function of x. Then as it is here, this variable x, we call it an independent variable. Independent variable. Then to get the value of y, you need to get x. So you take x, plug it into the expression of f to calculate y. Then we say y is a dependent variable. I hope I'm making myself clear. Is it clear? Okay. Then, of course, like I've already given, we've given this example of functions, but this one we're just using parameters a, t, and c. But a particular example, let's look at a particular example, like now I'm talking about examples. Examples. Now we'll talk about example of a function. In this case, I'll write here y equals to f of x equals to 2x plus 1. Listen to me very carefully. Here I'm just saying function of x. But what I'm writing here, I'm writing the expression of the function. How the function acts on x. How does the function use the x to build what? Y. Because y is dependent on x. Sometimes another name which you use in most cases, this x, we also call it the argument of the function. It's an independent variable. Also, we can call it the argument of the function. But it can be also more than, it can be more than the independent variable, it can be another function. But in that case, we say that x there is the argument of f, the function f. Then, this expression we wrote here, this one, we call it the functional notation of a function. Functional notation of a function. Functional notation. Always a notation is like for me it's like a word. Then the word has got its meaning, isn't it? What it means. So that's the functional notation of a function. So there we read this. How do you read this? This is read as I'm writing that what is read. This is read as function of x. That's how we read it. Once you see something like this, written like this, we read it as f of x, or function of x. So there with t, L was a function of t. Remember before we just said the expression there, we did t. So another expression of a function of yes? It's another function. No, yeah, notice functions, we name them using small letters. And the arguments also are written in small letters. But sometimes you can name a function using capital letters. So I can write g of t. That means that it's a function g which depends on t. I can write g of x. But everyday use as a shorthand of talking function, we normally use f of x. But now if you want to differentiate two functions, we want this to turn out differently, we can write one as f of x and write the other one as h of x and write the other one as g of x. Am I answering you? Okay. So the expression could be different. Like for example, I can write here g of x is equal to 3 to the power x. Then you've got another type of function there, which is different from what we got. So that is the functional notation. Are you understanding what is functional notation? Yeah. But as yet, I haven't even said what a function is. You notice that at times I've given you examples of what a function is, but I haven't said what a function is. All together? Okay. Now, let's maybe come to, first of all, before I define a function is, let me just, using the expression here, let me talk about something which I call evaluating a function. So what we have now, we just have an example of an expression which we call a function. Now we want to see what you mean by evaluating a function. Let's say we have got f of x equals to x squared plus 3x. Talking in simple terms, because I always want to talk in simple terms, things people can relate to. Talking in simple terms, what does this expression say? This expression says, whatever f carries in brackets, I will square it and I will multiply by 3. And lastly, I will add the two things. All together. Then that value is what is going to be, I'm going to call what? Y. Isn't it? So, at the end of the day, after the evaluation, we're going to have two values. What are we going to have? We're going to have x and the value of y. Then, basically, we're going to have what we call x, comma, f of x. What is f of x? is y altogether. So we're having the value where you are evaluating function, we're having the way you are evaluating function, which is the independent variable, and we're also having the value of the function. Then we'll keep it in pairs like that, isn't it? I'm still going to talk more about that pair there. Now let's say we want f of 2. What are we going to do? We have got to go to the statement. Let me call this thing the statement of the function. If that function states that we must do that, then what we must do, that f, we must do exactly what the statement says, now with 2 altogether. So what I'm going to do, who can tell me what to write there? Please say it aloud so that if the thing can record, so that when you listen to it later, you might remember what was said. Yes, my sister. We're going to say 2 squared plus 3. Yeah, that into, it doesn't sound to me like a good way of saying it. Just say 3 times 2, isn't it? Yeah, 3 times 2. Yeah, that's right. Because sometimes into can, I don't know, sometimes people can say maybe it's division, whatever. As I said, if somebody listening to you is not here, you might not know what it's meaning when you say into. Like when it's multiplication, they say multiply by or times whatever. Is that right? So now, if you look at what I've just written there, you can see that it has got the same skeleton with what I said there is a statement, is it? So, which means then you evaluate the function correctly. Hoping that you know that the brackets say meaning multiply, is it? Then we're going to have now 4. We know where 4 is from, is it? Yeah. Plus 6. Then we say this is 10. So now we can make a pair of 2 and 10. I hope you know this thing. You know how to graph a function, is it? So when you go to graph, you know then x is what is that, and the y is that, is it? Then I hope this is the reason why we are saying here. Let me just let me raise this a bit. Right. Take my pen again. Remember, we've got what we call a system of x's. We've got x there, and we've got y there, isn't it? Yeah. Then a function like this, I think all of us will know it's a parabola, but I'm not going to really sketch the parabola for this function here. I'm just going to sketch roughly what you all understand to be a parabola, isn't it? So once we have plotted these points like this, almost like we can never plot all of them, but we plotted these points like this, one example of them being 2 and a 10. Once you plotted it, I think you know that you can join them with some kind of a curve, which is a parabola, and you say that is what? F of x. Is that right? That's what we're plotting a function. So there, what we're doing there, we're just evaluating a function, isn't it? Okay. Now, I want somebody to evaluate the same function. Let me just see whether I can try this thing again. It disappointed me before. So, yeah, okay, good. It didn't disappoint me this time. Okay, now let's deal with the same function. Let's deal with the same function, and then now I want you to evaluate this function at, oh sorry, I didn't pick the pen correctly. I want to evaluate this function at h plus 1. What is that going to be? Can you push the pen against the paper and tell me what that is going to be? Push the pen against the paper. In other words, now our argument is h plus 1, isn't it? Then which means now we should work out that function and evaluate that function at h plus 1. Tell me whether this is correct, the way you see it here. Is this correct? It's not correct. What is short? It's squared. But if I don't want to use the square, is this correct? Okay. So that's what you must follow there. Now, work it out and give me the final answer. Can one person tell me? Yes, my brother? H squared. Remember here, this is a plus b. In this squared, is it? Which is a squared plus 2ab plus b squared, is it? So now the 5h is coming together with this 3h, is it? Okay, good. So we got 5h plus what? Plus 4. I think there will be 1 squared here, which is 1, plus 3 there, which gives us 4, isn't it? So then you have evaluated that function correctly. Good. Are we together so far? Okay. Right. Then let's just clear this. I think now it is important for us to define what a function is, isn't it? To know exactly how to tell somebody what a function is. Now, first of all, maybe schematically, we can say a function works like this. I'm using this kind of sketch, which you call, I think it's called a block diagram or a flow, whatever. In engineering, we use it a lot. A function is something more or less like this. And this box here, this black box, I call it black box. It's a system. So a function is actually an input. Input, output system. Tell me, when you input 2 in the previous function, what did you output? 10. So a function is a system like this, which is input, output system. All together. Now, what is important, like I said before, we have a set here, which we can call a set of inputs, but we've got a special name for it. In mathematics, we call it a domain. And then let's call it here x. That's the domain of the function. What do I call the domain of the function? All the possible things I can input to the function, and they give me a reasonable output. Altogether, I've said reasonable, acceptable. What wouldn't be reasonable? What would be reasonable? If I would take a grinding mill and put in some maize and output some cement, no, that doesn't look like a working system. Is that right? Yeah. I'm just trying to make you sense of what do I call reasonable. We'll talk about, we'll expand to on that later. Then we've got here another set, which you can call the range of the function. And then in the range, what sits in the range? In the range sits those values or those possible outputs of the function. So this side is input, that side is input. Then we draw schematically like that to show that we've got x here, we've got the outputs here, f of x. Like as you see now, there are two sets involved, x and y. So there are two variables involved. So in this case here, this is a function which we can say now here, y is equals to f of x. Tell me, how do you like this thing? How would you like to say? Let's say you invent your own machine. You invent your own machine in such a way that when you input maize, I will talk about maize meal because I grew up from maize meal. So it makes more sense to me. I hope it makes sense to you also. But everybody knows what maize meal is, isn't it? You take the grains, those grains, you input them in your machine. Today, you get flour. Tomorrow, you get meal. The other day, you get what? Cement. What are you be happy about that? No. That example is an example of what I can call a system which is not acting like a function. How does a function act? A function acts in such a way that if you put an input here, you must always get a unique output. Altogether. So I can say a function is a relationship between two sets whereby if I've got a member of this set, I can only associate that member with only a unique member in the other set. Something which acts like that is a function. Altogether. Yes? A parabola, yes, is a function. We'll check on that one now. Let's check whether it can give you two values. So guys, a function is a system which when given one input will release a unique output. Altogether. That is very important. That is very important. Now, let's talk about, let's look at examples which will make us feel using graphs like he's talking about parabola, that is a function or it's not a function. Okay, let's do this. First of all, let me do this. Okay, a parabola is a parabola, a function. Is parabola a function? Let's say take an example as an expression. A parabola is something like this. All parabolas develop from something like this, isn't it? And we know graphically from school that's a parabola which passes through that. Obviously, guys, this is a rough sketch, isn't it? You must see that graph as perfect as the one parabola we know at school in a book, drawn nicely, isn't it? Just imagine, your imagination can do that, isn't it? Now, give me, you said it can give you two values, isn't it? Give me a value of x which will give me two values of y.
No, but I can give you a value of two values of x to give you one value of y.
No, now you are moving in the other direction now. You are now moving from the other set y going back to x, which is another thing which we haven't talked about. We are talking about now moving from here to the other side. Altogether. We are still going to talk about what we are talking about now, but that's not true. But remember to just make it quick because you are familiar with this, I think. Now, if this is a function, y is equal to that. I can just say that's a relationship between x and what? This is a relationship between x and y. But there's also another relationship between x and y, which is similar to, which is related to this, which is y is equal to the square root of x. Where the graph, let me check. Not necessarily. We are far away from inverse, but what you are saying is not very, very wrong. We are going to talk about that. Let's say the graph now will be like this. Altogether. Are you sure? That graph is not a function. Why? Because if I now say, let's call this thing again, sorry, let's still call this thing f of x. If I now give f of x, give it 4, this f of x will calculate the square root of 4. this machine will give me 2 or minus 2. Then if you follow the argument before, we said a function is a system which when given a single input, if a given input, it must give me a unique output, but this output is not unique altogether. Then this is not a function. Convinced? Okay. Okay. So that's the thing. And another maybe that's just there on that spot. We can I can give you what you, if you have graphical test of a function, graphical test of function. Let's say graphical test of a function. Now I'm taking a graph and testing whether the graph is a function altogether. What we normally use, we use a parallel to the perpendicular, isn't it? We use a parallel to the perpendicular. Let me pick another color there and say that. If we use a parallel to the perpendicular, that green line there, you can see for the black graph, that thing gives us for this x here, for this x which is there, it gives us only a single point whose y is that and the x is that. Then there we've got we've got x comma f of x, and that f of x there, value there is unique, isn't it? But when you come to what? To the purple graph, that same x will give us this, and they will give us that, isn't it? The two y's. Now if that x is 2, for the purple graph, that will 2 and minus 2. Then, which means this one is not a function. Not that I'm writing in capital letters there. Not a function, to emphasize. This is not a function. So I've given you a graphical test, and the other thing, you can compute the values and see if you put the value like 2, you get 2 values. But like this one we computed there, we saw that get 2 values. That's it. That's when you're using the expression. But on the graph, this is what you use. You just draw a parallel to a y-axis. If the parallel to y-axis cuts the graph at 2 points, then the graph is not a graph of a function. Any relationship between two variables can produce a graph, but that doesn't mean that any graph is a function. Are we together? Okay. I hope I'm making myself clear. Okay. I haven't annoyed anyone so far, no? Okay. Alright. So that's good. Then let's clear that. Are there any questions? Are there any questions? No, that one we can talk about it, but it's not very important now. You see, a function can be one, I think we are trying to say 1 to 1. 1 to 1, 1 to many. Okay, that's something like that. I'll just quickly explain it if you really want me to explain it. Okay, let's see this. 1 to many. That relationship which we have just looked at of 4, square root of 4 being plus or minus 2, is an example of 1 to many. But in that case, but it's 1 to many, but which is not really a function. Isn't it? We saw that. That is 1 to many. But now, if then there's many to 1. There's also many to 1. If you look at the parabola, f of x equals to x squared. If you talk of y equals to 4, there's many to this. What is that? It's 2 and minus 2, isn't it? But as 2 minus 2 alone is minus 2 to 1, which is 4 only. If you look at 2 alone, is 2 to 1, which is 4 only. It's not just to 4 and to 6, it's to 1. Isn't it? That is 1 to 1. But there are some the functions like this. Y is equal to x, where you draw the graph like this. That function is always 1 to 1. You cannot get something like many to 1 or whatever. Then it's a 1 to 1. I think that's the thing. Okay, another question? Another question? Yes?
So you talk about an argument. Can I ask about
a conjugate? Yeah. Let's talk about conjugate when we talk about complex numbers. Yeah, but the term conjugate is used in many different situations. But for your case, I think it will be more relevant when we talk about complex numbers and talk about conjugates and all those things. That's right. Okay. Now, so let me another question. Sorry, before I, okay. So if there's no question, then let me just carry on this thing of a function again. Let me write the function. Right. Actually, a function, if you saw the function which you wrote before, let me write this function here. Let's say f of x equals to x squared plus 3x. This is a function which can make me talk about the system and the subsystem. Because what is a system, first of all, guys? Do you know what is a system is? I know people always use the word system. What is a system? When you say system, sometimes people even talk, even when they're talking about politics, they say, hey, this system is not working. What is the system? What is this thing system? Sometimes even the hi-fi, people call them system. What is a system? You see, how many times we use words which you don't understand? Right. A system, in simple ways which can be understood by anyone who doesn't need to go to university, a system is a collection, we can say maybe a collection of instruments or a collection of machines which are set up in such a way that they perform a task. Did you say what is it? I said a task. I didn't say tasks. But every time you are looking at a system, that system is supposed to perform a task. Now it's a unique task. Altogether. So that's why that's the link with the notion of the concept of function. So now let's talk about something which more or less involves subsystems. Obviously, subsystems will be connected together to form a bigger system, isn't it? And I'm talking about in terms of this thing. In terms of this thing, the input will come here, maybe as x, and the output will come here. Definitely, I said maybe there, definitely as x, then as y. But if you look at this function, it's involving different systems which are doing different things and they're built up together. So in the first stage here, what's going to happen? I'll just write SQR for square. So when x comes in here, it will be squared, would it? Then but x will also pass maybe and come to this box here. So that. But when it gets there, it will be multiplied by 3, isn't it? Take that times 3, isn't it? Then, when the process passes to the next stage, it's going to come here, find the difference of what? According to the statement there. It's going to find the difference, I just write the diff for difference, the difference between x squared and that, isn't it? Then when it does that, then it delivers y. Altogether. So in other words, this squaring is a function on its own, and this times 3 is a function on its own, but these two systems of x squared and 3, they've been like cascaded, they've been done independently, and then later build a bigger system using the two of them, isn't it? So then we've got a function there. So what I'm trying to say is that a system as a black box like this might have inside subsystems, isn't it? Which are all acting on what, on the input which you put in. So, but I think actually maybe this, I took this example in the book, but as I'm thinking about it now, I think it's not the best way of representing it there. Maybe the best way was to put 3x and the square a bit parallel, isn't it? Then later you take them to one system where you put, because what's going to happen here, let me just draw it well, just to make sure that you see what I'm saying. I could have put here a square here. I took it from the book, I didn't think like I'm thinking now. Then I'll put it times 3 here. So x will come in here. And because this thing is at the same level, x goes there and it goes there as an input, is it? That is within this big system. Then this is going to get an output there and an output there. But it comes to this smaller another system. Then it says here now x squared minus 3x. Then what does it do now? Then it takes out something out of the whole system, the bigger system. I want to say nothing. So those small boxes inside there, they become subsystems altogether. But each one of the system there is going to act as a function. How many outputs is going to put? Unique output. Altogether, guys. Okay. Now, let me come back on. Remember I said the output must be a reasonable, something which makes sense. That's right. So let's come and talk about the domain, more about the domain and the range. The range, obviously, we're talking about the input. Now, if I've got f of x equals to x squared plus 2, can I ask you, tell me, first of all, I assume that you guys, you know about numbers. Give me an example. Natural numbers. Natural numbers? What are natural numbers? Natural numbers 0, minus 1, minus 2. Come again? Natural numbers? Say it, speak up, speak up. Speak up. No, it's just waiting for the lecture to end in 5 minutes. Speak up. Natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on, isn't it? Then we come to integers. What do we have there? There we said we have got 1, 2, 3, and then here we've got 0, we've got plus, minus 1, plus, minus 2, plus, minus 3. Remember that one goes in 2 directions, isn't it? I'm just writing there because I don't have space, isn't it? Then we've got numbers like rational numbers, is it? Which are numbers like, is 0 rational number? Yes. Yes. Can you put it as a ratio? How do you put 0 as a ratio? What is 0 equal to as a rational number? Aha. First of all, a rational number, a number here is a number, remember, is a number which is P over Q. P must be an integer, and the Q must be an integer, and the Q must not be equal to 0. Now, 0 itself is equal to 0 over q, where q is not equal to 0, isn't it? So then 0 is a rational number, isn't it? So is 1 a rational number? Huh? What is 1 as a rational number? 1 over 1. I can just say it's a over a. Isn't it? Where a is an integer, not equal to 0, isn't it? Because if you include 0, this is not a number. This, when a is not equal to 0, this is not a number. And this is not a number. So now, when I'm saying a function must give something which is reasonable, if I'm talking in terms of functions like real, we're using real numbers, then I mustn't get anything like this. Anything which gives me something like this is not in the domain of the function. I understand what I'm saying? It's not in the domain of the function. Even when I'm dealing with a square root, this is not in the domain of the square root. That minus 1 is not in the domain of the square root, is it? So when I'm saying something is in the domain, you must, when you choose numbers and say these numbers are in the domain of the function, you must be sure that they don't produce any of this type of nonsense. Are we together? So in other words, when you evaluate the function and get any of these kind of things, then that value where you're evaluating is not in the domain of the function. So tell me now, what is the domain of this function? What are you supposed to check? You are supposed to check whether is there any value of x which is going to give me this type of nonsense. Is there any? No? No. Yes. What I say? No. No. I think it's no. So which means the domain of this function is all the real numbers. All together? Okay. We're going to take it from there. I think it's time up. That's the alarm going on there. It's time up. Let's stop there and we'll take it from there next time.